So what is regularization? Well, regularization is basically techniques for improving generalization. Let's look a bit at how your training process is going to work. Basically, what's going to happen is, to begin with, you're going to be in some sort of an underfit situation. Okay? So for example, you will go ahead and, okay, so we're in this situation. We just do training for a couple epochs. And we want to get better both test and validation losses. So lower test and validation losses. So one thing we can do if we're underfit is train more. So train longer. Another thing we can do is increase the power of the model. So for example, if we were in the universe of polynomials, we might want to increase the degree of the polynomial. If we're in neural networks, which we'll talk about a little bit later, increase the number of parameters. Eventually, we're going to get in some situation where we are no longer underfit. And then we're going to be overfit. So when we move from underfit to overfit, how can we get out of the, back up again. So what do we do in this underfitting? Well, what we do is we keep training longer and longer and longer and longer. And eventually, we'll probably move to being overfit. Or we're going to increase the power of the model. Okay? And then eventually, we'll move to being overfit. So some combinations of these things. Right? And then, how do we fix overfitting? Well, for overfitting, one thing we can do is add more data. And another thing we can do is use regularization techniques. So perhaps these arrows aren't quite right? Because we're not saying that if you're overfit and you add more data, you necessarily stay overfit. So maybe really what it is you add more data also may lead you to become underfit. And using regularization techniques also may lead you to be underfit. And similarly, increasing the power of the model may take you here, and training longer may take you here as well. So it may be enough to train one more epoch to all of a sudden become overfit, or it may not. The adding more data is in some ways the best way to solve overfitting. So if you are training on 100 examples, so if you have 100 training examples, and you start becoming overfit, then if you increase to 1,000 training samples, you'll probably do better. And if you can increase to 1,000,000, you'll do even better. And if you can deal with, let's say, 100 million training samples, then you do even better. And as you increase the number of training samples, you can also be increasing the power of the model. So what's going to happen is, right, as we look at, let's say, so this is the loss, and this is the training. If we have a low-powered model, this is the test loss, low power. If we have higher power model, that is, we have more parameters in it, so it's richer and going to represent more things, then we maybe get a lower test loss, right? So maybe they'll asymptote lower. So here we have test loss. So one thing we're trying to do as we are training is underfitting tells us basically how low the test loss is going, right? If the test loss is staying high, then we need to either be training more or we need higher power. Adding more training data doesn't help us in reducing that loss. And then, so we basically say, what's our target on our test loss? How far down can we go? How do we reduce this test loss? We reduce the test loss by training longer and increasing the power of the model. Okay. The problem, though, with both of those, both increasing the power of the model and training longer, tend to cause overfitting. And so we solve the overfitting by adding more data or using regularization. The problem with adding more data is it can be expensive, right? We need labeled data in our case. Labeled data meaning if we've got a picture of a happy face and we're trying to do a happy sad recognizer, we need to come up with a label. So this is X, and we need to come up with a Y that says happy. Okay. How do we get these labels? Well, normally we need humans to do this. So let me give you an example of a data set called ImageNet. This was used as a basis for competitions in the 2010s. So from around 2000, well, neural nets really started winning this, I think it was in 2013. So 2012, 2013, somewhere in there, and there were just substantial improvements over the next several years. But the ImageNet data set is about 1.2 million labeled images. And they're labeled with one of 1,000 categories. So for example, one category is, I think, I'm not 100% sure, I don't remember these, but let's say German Shepherd. And another is bee. And another is bus. And another is tree. Okay, so we have all these categories that these images are labeled in. How did we get the categories? Well, first off, where'd the images come from? Well, this was done at a university, and they were basically just downloaded from the internet. But they don't come with labels. So where did we get the labels? Humans. Humans did that labeling. Did they force the grad students at that university to do the labeling? They probably did some of it. They also spent a little bit of money. So they used Amazon Mechanical Turk. Amazon Mechanical Turk is a service that actually farms out small little jobs to humans. So for instance, these humans would see like a picture. Of course, a real picture. This is supposed to be a cat. And so they had these 1,000 categories and they had to label into one of those 1,000 categories. And they might have been paid, let's say, 3 cents per image they label. Okay, so they just shoot through and do those. And in order to ensure, right, maybe you have a Mechanical Turk, what they're called a Turker, who wasn't too careful, then maybe they actually send every image out to be labeled 3 times. Right? And then they can verify that they all agree on what the label is. So this is a very important data set, and this was used as this competition. Now this is pretty much considered a solved problem. We have here our diagram that we've been using, looking at how the gradient descent works. The regularization can occur really at any point in this diagram. So regularization can be done with changes to X or Y or the loss function or the optimizer or actually theta itself. The only one I can't think of right now is F. I take that back. I can think of changes to F as well. So we're going to look at a bunch of different techniques having to do with making our model be more generalizable.